Hey everybody, in this video we're going to be talking about the normal curve, also called the normal distribution. We're going to be looking at just the basic properties of the normal curve in this video, and kind of how the standard deviations correspond to the mean, what their distribution looks like, that kind of stuff. So let's start with some symbols. The first one is going to be our symbol mu. It's a lowercase Greek letter, and that represents the mean of the data that you're looking at. Or also remember, mean means the average. Another symbol is going to be this lowercase sigma, and this is our standard deviation. So we'll be talking a lot about standard deviation. And the last one is sigma squared, and this is the variance of the distribution. Now, we don't use variance as much in the next video, in this video and the next couple after this, but what happens is we use this in our notation. Why we use this in our notation, and then we'll see that with our calculators we use standard deviation. I don't know why we use the differences, but that's kind of the way that it is. It's an unfortunate circumstance that's the way that it is, but so be it. Okay, so let's label this up. So here in the center is our mean, the mu. That's going to be right in the center of your normal curve. And actually, if you want to know a little bit more, the mean, the median, and the mode are all the same for a normal curve. So that's something to also keep in mind, that the mean, median, and mode are all the same for only normal curves or normal distributions. Then each of these other tick marks, these are each represent standard deviations on either side of the mean. So on the right side we've got positive standard deviations, on the left side of the mean we've got negative standard deviations. And this just represents how the data is distributed based on standardized units or standardized values as we go to the right and to the left. Alright, so if this is right here centered on the whole curve, the mean is, that means that this whole side here is going to be 50% of all of our data. So that's going to be 50% of the data less than the mean or lower than the mean. And on this side we would have 50% of the data above the mean. And really what this kind of means as we start looking at this a little bit further, that we're talking about the area under the curve. Now that gets into a little bit more of calculus, but we use that term area under the curve interchangeably along with 100% of the data that we're talking about. So we could be talking about data, we could be talking about the area under the curve, or we could also be talking about or considering probabilities. So all three of these things are kind of interchangeable as we're talking about this space underneath the curve. And we'll use the mean and the standard deviation as reference points to help kind of determine what is that probability, what is that area, what percentage of data are we talking about. So all of this is going to really focus on that space underneath the curve. Alright, so let's look at another curve here. So we'll label up our means and our standard deviations, and let's look at how this data is distributed when we look at it in terms of the standard deviations. So one standard deviation on either side of the mean. That means this space here. And when we look at that whole distance, from -1 standard deviations to 1 standard deviation, or as we say, 1 standard deviation on either side of the mean, we also use that terminology, that is going to be approximately 68% of the data. Now there's some decimals in there, but when we're talking about this, we generally use just general notations or approximates, and we say it's approximately 68% of the data. Which means that 34% of the data falls between the mean and the first standard deviation on the right side of the mean, and 34% of all of the data falls 1 standard deviation to the left of the mean. So that's just good to kind of get a bearing of your percentages, because we could say looking at comparing this curve and the curve above, and we want to know how much data is less than 1 standard deviation above the mean. Well, we know all the way up to the mean is 50% of the data, and now we know from the mean to the first standard deviation is another 34%, so we know that 84% of all of the data falls from the first standard deviation and below. All right, so that's kind of like the idea that tends to come with these types, some of these types of problems, is looking at the percentage of data when we're referencing the mean and the standard deviation. Okay, so let's look at our next ones. So 2 standard deviations. So we're talking about this space and the yellow space included. So this distance here is going to be 95% of all of your data. So when we're looking at one side, we're looking at both the yellow and the green shaded space, and that will be approximately 47.5% of all of your data. And same on the other side, if you consider just the yellow and the green to the left of the mean, that will also be 47.5% of all of your data, approximately. And then if we go out 3 standard deviations, and we're talking about these little bits as well as the yellow and green, now this whole distance from -3 standard deviations to 3 standard deviations, positive and negative, all inclusive there, we're talking about 99.7% of all of the data of a normal distribution will fall between 3 standard deviations on either side of the mean. Now, we could look at all 3 of these different shadings and determine that that's 49.85% of all of your data. But when you get to this quantity of data, what we usually end up looking at is the part that's not included. So the part that's bigger than 3 standard deviations. And that's going to be 0.15% of the data is greater than 3 standard deviations, and similarly 0.15% of the data is less than -3 standard deviations away from the mean. So when we're looking at these things, again, the yellow and the green, we might be looking at those values, but when we get to the orange or the blue line here, we tend to look at what's outside of the means. I'm sorry, what's outside of those standard deviations. Just kind of knowing on how questions tend to come out. That's why we go that way. So the notation that we use a lot of times when we're discussing a normal distribution of a random variable, this is kind of tying in with probability, is x, then this little squiggle is approximately normally distributed with a mean and a variance of some value. So again, we come up with this sigma squared, which is our variance, but when we talk about the data, most of the times we're going to be using the term standard deviation. So just think of that, if you see that value, you have to take the square root of that. So that way you know that when you're using this notation that we are talking about the standard deviation or the variance, right? You're going to have to be able to bounce back and forth between those. Alright, so let's look at some other curves here. So let's say we've got these 3 curves here, where we've got x, the random variable x sub 1 is approximately normally distributed with a mean of 5 and a variance of 2. A variance of 2 squared. We have x sub 2 normally distributed with 10, or we can even say a standard deviation of 2, right? Because we know we can bounce back and forth between these 2 things. And x sub 3 is normally distributed with 15, a mean of 15 and a standard deviation of 2. So what this is showing us is that we have different means, but we have the same standard deviations. And even though we have different means and same standard deviations, we could still talk about the data in relation to each other using the standard deviations as a reference point. We'll look at some examples of this as we go into other videos, but really that's being able to say that we can compare 2 different sets of data that are normally distributed and compare these unidentical data sets to each other in relation to standard deviations in the mean. So if I had heights of girls and heights of boys at a given age, we know that just through genetics that boys tend to grow faster than girls in height, and they tend to be taller than girls in height, but we could still say, well, girl X is within in the 1 standard deviation of the mean, and boy Y is within 1 standard deviation of the mean. So in relation to their own groups, they are in the same spot, even though their actual heights might be different from each other. So a bit of a tangent there, but kind of the big idea for this, and we'll get into that more in other videos. So another image that we have would be one that looks like this. And this is going to have x sub 1 being approximately normally distributed with a mean of 5 and a standard deviation of 1. X sub 2 has a mean of 5 and a standard deviation of 2. And x sub 3 has a mean of 5 and a standard deviation of 3. So again, all of these things have the same mean, but now we have different standard deviations. And again, this is a huge idea with this, that all of these things, whether we're talking about the curves on the left or the curves on the right, the curves up above, they can all be compared to each other with regards to the standard deviation. So that's kind of a really powerful tool to be able to do that no matter where this data is placed along an x or y axis, that as long as they're normally distributed, we can compare them with other shapes that are also normally distributed. So kind of a cool idea. And again, we'll look at some of those ideas in the next video. So hopefully this gives you a nice overview of the normal curve and the normal distribution and some of the notations that we use, the percentages of the data, and we'll talk more in the next video.